Boom. Okay, just hold that thought for 1 second. So guys, we've never done this together, but it shouldn't be surprising given how we run general chemistry. We will always start the day by answering questions from the previous day's homework. Now, from general chemistry, you probably remember that there were very few questions that God asked. Many times there were crickets chirping, or I was trying to lead the conversation about what questions do you have. Frankly, simply because general chemistry, I think you would agree, is so straightforward that either you understand the material, or if you're struggling, you probably don't know enough to know what you don't know. You know what I'm saying? Guys, AP chemistry is completely different. These questions are unique. They always require synthetic thinking. You notice they don't line up in columns. It's not like if you can answer question number 1, you can do 2 through 10 because they're all the same. They're all different. They all come at ideas from different angles. And so guys, consequently, I would propose to you that this is the most important part of the day. Yeah, we are going to learn new material, but guys, it's not until you really get to engage with the material that you really then begin to get an appreciation of what it is you're learning. And so guys, we always start here. We always answer questions. We will do this until your questions have been satisfied. But guys, understand this does not take the place of coming and getting help if you need. Nathan and I sat down for 20 minutes this morning and worked through some of the conceptual problems because frankly, maybe you didn't know that nitrogen was blue and oxygen was red and carbon was gray and hydrogen is white, but you do now. So guys, understand this is a great place to start the day. So grab your books, open up to the end of chapter 3. We will always do this together. So guys, there's only one rule. That's not true. There's 2 rules to this time in this class. Rule number 1 is we're all working together. So if you have a question that isn't the one that's immediately being addressed, you'd be a fool to not join the conversation. Because guys, we end up talking about things that may not even be contained within the question. So this is a great place to sort of get your thoughts moving. So we'll always be doing this as a group. But then guys, the second rule is this. When you ask about, say for example, question 5, I don't know why, but it drives me nuts. Please don't call it 3.5. We all know what chapter we're in, so we're just going to call it question 5. So, with that said, Spencer, it sounds like you have a question.
Yeah, why is it like all the elements have the same color as the same element has different colors from others? Like, why do we have to choose a specific color?
Oh, so when you say colors, you mean the colors of the circles that we use to represent them? So it's actually pretty universally accepted. So if you remember last year when you guys were mucking around with these, and I know that probably you don't, but right, so that's the idea. So black is always carbon, red is always oxygen, white is always hydrogen, and then blue is always nitrogen. Yep, so now you know. So guys, what other questions do you have? Please. Yeah. That's a really good question. Yeah, and actually, Nathan, I meant to mention this to you, and I didn't. So guys, on 5A, you'll notice that it actually gives you the structure. Is it glycine or something like that? It's one of the amino acids. And it gives you the ball and stick structure. And then it says, write the formula for this compound. So does it matter what order they go in? And the answer is yes, but they won't hold you accountable for it. So that molecule is actually, it contains carbon. It's an organic molecule. And for those of you that are getting into chemistry, your sophomore year, you'll be doing this, which is organic or OChem. And in OChem, you'll actually learn all the rules about the orders that these go in, but they don't hold you accountable for that in this class, in AP, because this is not organic, it's inorganic, so you don't know the rules. So there are, yes, it does matter, but they won't hold you accountable to it. So, what else, y'all? And it doesn't just have to be on this page, although if there are questions on this, it's a great time to do it. Good, Ernie? Yeah? Yeah, that's a really good question. So how much do you need to write? And here's one of the things, well, it becomes apparent quickly. For many of you, the thing that you're going to struggle with in this class is your ability to write efficiently. I've had students that would write paragraphs to answer simple questions, and you simply don't have time on the AP test. With that said, what I will do in the homework solutions is many times I will write a lot more than I need to, because if you didn't know the answer was NO2, if I just put NO2, that's not enough to help you figure out what you didn't understand. So a lot of times I write a lot more than is necessary because I know you're at home struggling with these. And so don't think that you're, so yes, in number 5 you could just put NO2, because the question says, what's the empirical formula? The thing to look for in this class is if it says justify or explain. If you see either of those two prompts, then you need to do more than just a one-word answer. Yeah. Guys, what else? Please. Okay. Yeah, so let's do this. So are you familiar enough with the question that we can talk about it? Okay, so, and Nathan, thank you for coming in this morning, because frankly, because we talked, I know all the questions, which is really helpful right now. So fundamentally, the question in 3 is this. You've got a bucket full of, is it nitrogens and oxygens? Okay, let me go back and look at it. So you've got a bucket full of nitrogens and oxygens. So I'll just write in a few. But you've got something that looks kind of like, and it's just a smear of these things, right? And it tells you that this is the product of a decomposition. So you take a compound, you blow it into its atoms, which are diatomic molecules, and you end up with this. And so in part A, we counted, and we figured out the empirical formula by finding the nitrogen to oxygen ratio simply by counting dots, right? But then part B says, given that we know that this is NO2, which meant that for every nitrogen there was 2 oxygens, do we then know the actual formula of the molecule? And so the reason, the answer is no. The reason is because of something like this. So imagine that we had a similar box. And inside this box, rather than drawing circles, I'm going to write abbreviations. Like so. So imagine this was what was in the box. So we have carbons, hydrogens, and oxygens. And if I did this right, it should be a 1 to 2 to 1 ratio. So we've got 1 carbon, we've got 2 hydrogens, and we've got 1 oxygen. So similar to number 5, we can figure out the empirical formula just by counting the pieces. But then, if you're making the link to how we originally learned about empirical formulas, we then said this. This could be C5H10, that's an H, and O5. This could be C6H12O6. This could be C11H22O11. It could be any sugar. So the idea is that we can establish the ratio, that's the empirical formula, but we don't know the exact molecule because all we know is a ratio, we don't know direct amounts. Does that make sense? So then the question becomes, and guys, you should be able to answer this question. What do we need to know in order to take the empirical formula and turn it into the molecular formula? Go ahead, Matt. Not the density. Which mass? Of the molecule. We need the formula mass. Do you remember when we did that at the end of class last time? So with that information, if we knew the formula mass, we could then figure out the structure of the molecule, but without that we can't. And again, we will do that in lab in about 3 weeks. So, guys, what other questions, not just on these, but on all of the assignment that you could actually do?
Wait, how can you do like NO2? Like it doesn't add up to an even number. You can't do that.
What doesn't add up to an even number?
Like the numbers for N plus O plus O, like those don't add up to an even number.
It doesn't need to.
It doesn't.
H2O doesn't add up to an even number. Yeah. Guys, what else? Please. Hold on a second. Let me do some mad clicking. Were we able to do 37? Okay, go ahead. Letter C? Okay, so let's talk about it. So probably the first thing that you noticed, and this is really common in this class, this is a compound question. Letter A leads you to B, leads you to C, leads you to D, which is really common. But if you look at number 37, it says, okay, and let's just do from the top. So it says the molecular formula of allicin, the compound responsible for the smell of garlic, little did you know, is this. So what is the molar mass? And you were probably okay with that, right? Just add them up. Then letter B says how many moles of allicin are in 5 milligrams of the substance. So it was a dimensional analysis problem, and we go from there. So then letter C says this: how many molecules of allicin are in that same amount, the 5 milligrams? So what I did was this. Up here in letter B, we had already calculated how many moles of this molecule are present in the 5 milligrams. And so if you remember back in the day when we started doing moles conversions, we had this table. Is that familiar? And does it sort of jog your memory? So this was moles, this was mass, and then this was particles. And for particles, we included things like atoms and molecules and formula units and stuff like that. And the conversion between moles and particles, we decided, was Avogadro's number. This conversion is the formula mass, which you figured out in part A. But to get from moles to particles, we need Avogadro's number. And that's exactly what I did here, is I said, okay, if I know the number of moles, and I do because of this, then 1 mole is Avogadro's number of particles, and you just go from there. Is that okay? Now understand, what if we hadn't done part B? What if they had just said how many molecules is in 5 milligrams, but we didn't do part B? Well, if that was the case, then it would actually become a 2-step conversion where we'd go milligrams to moles and then moles to particles. But that's basically what they did in B and then in C. Is that okay? What else, y'all?
What if we get a slightly different number, like 1.25 instead of 1.8?
So probably the difference is some intermediate rounding right here. And guys, this is for all of you. In AP, on the AP test, you have to be within 1 significant digit of the correct answer. So if the correct answer is 1.86, you could have anywhere between 1.9 and 1.7. So you could be on either side of that by 1 significant digit. So you would have been just fine. What else, you guys? Are we okay? Please. Oh, yeah. So like up here, is that where you mean? Yeah, so here's the idea. So formula mass, let's say carbon. Carbon has a mass of 12, but it's 12 grams per mole, like so. So the mass of carbon is 12 grams per mole. But what we can do is, and maybe you know this from math, that the negative exponent flips it over. So we can also write it like this. And the -1 exponent means in the denominator. And so that's all that's doing, is allowing you to write on one line what should be in the denominator. Yeah. Guys, oh, please, Annika. Well, that could be my fault. Let's look. 19. That's going to be easier to get to from my keyboard. 19A. Okay, so it looks like the combustion of propane. No, cyclopropane. Let's take a look. So balancing 19A. Oh, it doesn't even tell you. Okay, but it is just a simple combustion reaction. So we've got C3H6 combusting in oxygen to produce carbon dioxide and water. So did I screw that up, or is that right? Is that right? Okay, so let's just try this together. So if I were balancing this, I would say 3 carbons, 1 carbon, so I need a 3. Then I would say 6 hydrogens, 2 hydrogens, so I need a 3. And then what I realize is that this creates an odd-even conflict, because that gives me 7 oxygens over here, and it gives me packages of 2. Does that make sense? So then what I do is they say, okay, I know eventually I've got to have an even number of oxygens because it only comes in even-numbered groups. So to fix that, I double the source of the odd number. So my odd number is coming from here, so I'm going to replace that with a 6, and then I'm going to start over. So now if I've got 12 hydrogens, do you see where I say 12 hydrogens? That means that I need a 2 here. That then gives me 6 carbons, which means I need a 6 there. And then that gives me 18 oxygens, which means I need a 9 here. I pray that's what my answer says. Is that what I said? Oh, good. Yeah, so that's the idea. So that's that odd-even conflict to look out for. Guys, anything else? Please. Good question. So let's talk about that for a minute. So in all of these, as they're written in the book, they give you the subscripts that tell you the phase, solid, liquid, gas, aqueous. You never have to put those on the AP test. We'll never do that. What you'll find, well, there could be a question that says, in this reaction, what phase would carbon dioxide be in? But they never have you write it as subscripts, so you never have to worry. And if it's included in the book, you can leave them off. What else, y'all? Yeah? Oh, so, yeah, it just means dissolved in water. Yeah, but what you're going to find, if you turn your book, guys, do this with me. Turn your book to chapter 4. Turn your book to the very first page of chapter 4. Annika, your question is timely. It's everything we're going to do in chapter 4. So, and we're going to start that even today. So, when we now hear the word aqueous, we just mean chemistry happening in water. And most of the chemistry in this class will. So you're going to see that chapter 4 is just a huge catch-all. We're going to talk about acids and bases. We're going to talk about precipitation reactions. Remember when we mixed the bottles together and we formed the chunks? So we're going to do precipitation. We're going to do acid-base. We're going to do a little bit of what's called redox chemistry. And that all fits under the umbrella of aqueous, which is what we'll start next time. And even a little today. So guys, anything else about homework? You see how this actually turns into valuable time because we talk about a bunch of stuff that isn't directly referenced in the questions. This is good. But guys, we are not going to record your homework performances. We do it just like general chemistry where you're not giving me a score. You're simply saying yes or no to the question, is it done? And did you get your questions answered? Because again, guys, this is practice, and we want to support you through that process. But we're not going to do that today because what we are going to do is finish the assignment. Does that, you remember we didn't get done last time? Okay. So guys, you can put, well, it's up to, you're going to have actually a fair bit of time to work on your homework today. So let's put the homework, grab your notes from last time, and let's just pick up and dig in. So, is it warm in here? Okay. My thermostat, my internal thermostat is totally broken. So I can never tell if I'm warm or if I'm just weird.
And what happens if you miss questions? Do you still get to?
So remember, Spencer, the question isn't whether you're getting them right or wrong. The question is, do you now understand? And if you can say yes to that, you are gold. So, guys, remind me if you would, please. Is this where we left off? Where we figured out what ethylene glycol really was? So we have not talked about limiting reactants yet. Is that true? But not mathematically. Is that right? Okay. So guys, this then is where we're going to pick up. And let's anchor ourselves, if we could, to the book. Okay, so guys, this puts us on page 96 in the book. All right, so starting there, gang. Let me gather my thoughts for a second. Okay, we're gonna go slower than ever. So, guys, now that we've got through these ideas of moles, balancing equations, all these other things, it's at this point in chapter 3 that these ideas come together. And we start looking at more complicated or high-level ways of thinking about how we can describe reactions mathematically. And as we do, we start talking about what the book calls quantitative information in reactions. And this is where we start solving what are called mass-mass problems. So guys, mass-mass problems, and you can certainly reference the book as you look at this. But guys, mass-mass problems are problems where we can answer the question, if this much stuff goes in, how much stuff comes out? And we will solve one of these in a couple minutes. But I just want to remind you that last year we did solve mass-mass problems. But we'll come back to this in just a minute. I do, however, want to pause for a second and talk about limiting reactants. So guys, let's do this conceptually first, and then we'll do it mathematically. So you may remember the idea, I don't know if Miss Call did this, but it's sort of a fitting example of how this all works. So guys, if you light a match, you understand now that this is actually a combustion reaction. So the cellulose is, well, it's like a combustion reaction. The cellulose is burning in the presence of oxygen. There's carbon dioxide and a couple other things, water and others. But guys, you know eventually that this match is going to go out. I'm not going to let it burn all the way out because it will burn me before it goes out. But guys, the idea is when the match goes out, what made it go out? Let's use the word. What limited the extent to which that reaction could take place? You run out of paper, right? So obviously there's two reactants. It's paper and it's oxygen. And we know that we ran out of paper because if the other was the limiting reactant, we'd all be dead, right? But you understand that's actually how a lot of people die in fires. They don't burn up, they suffocate because the fire is actually consuming all of the oxygen in the house and there's not enough left to breathe. But guys, the idea here is that a limiting reactant is the substance that you run out of first. Again, you may remember the silly example we used last year of building bicycles. But guys, it's a very, very important concept because the reaction ceases when the limiting reactant is gone. The question becomes, how do you know which substance is the limiting reactant? So guys, if you want to, I don't know if you want to write down the steps, But I would like to actually go through this with you so that we can actually do some calculations and figure this out. So guys, when we calculate limiting reactants, what we're going to do first is we're going to convert mass to moles. The idea is that when substances react together, they react together in molar ratios and not mass ratios. And we'll look at that more in a minute. Then we divide by the coefficients from the balanced equation because that takes into account the idea that it's not always one of these bonding to one of those. And then whichever number is smallest is actually the substance that's the limiting reactant. So guys, whether you're choosing to write this down or not, we're actually going to solve a quick limiting reactant problem just to sort of get the juices flowing. You guys ready to go? Can I make this go away? All right, so guys, in your notes, please write down the synthesis reaction that represents the formation of water from its component elements. Let's do that again. In your notes, please write down the synthesis reaction that represents the formation of water from its component elements. So guys, that was a pretty rich sentence. Let's parse it together and see what we can figure out. So, the first thing you heard was synthesis reaction. What do synthesis reactions do? Put stuff together. How many products do they have? One. So, the synthesis reaction that forms water. So we know that our product is water. But then you'll notice that the sentence went on and it said from its component elements. So guys, what is water made of? Hydrogen and oxygen. But why is this wrong? They're both diatomic. So guys, do you remember the diatomics? Let's go back and look. So you will never see iodine, bromine, chlorine, fluorine, oxygen, or nitrogen. You will never see, or hydrogen, you will never see these 7 elements by themselves. Iodine, bromine, chlorine, fluorine, oxygen, nitrogen, and hydrogen are what are called the diatomics. They always bond to each other if there's nothing else to bond to. So that means that you'll always see this. Now we need to balance it. 2 hydrogens, 2 hydrogens, 2 oxygens, 1 oxygen. So we needed 2. Now guys, here's the question. Say that we take a balloon and we shove 5 grams of hydrogen, 5 grams of oxygen into the balloon and light it on fire. Which one do you run out of first, the hydrogen or the oxygen? So again, 5 grams of each, shove it in a balloon, touch a match to it, it explodes, the product is water. Guys, the question is, which one do you, what did you run out of, the hydrogen or the oxygen if you start with 5 grams of each? Well guys, this is the way to figure it out. You go 5 grams of hydrogen and 5 grams, not of nitrogen, and 5 grams of oxygen. So guys, what do we do next? What's our first conversion step? Convert to moles. Why is it important to convert to moles? Guys, think through this with me before you write. Why do we convert to moles? And the reason is this. When we make water, it is not 2 grams of hydrogen bonding to 1 gram of oxygen. These are not gram ratios, they're particle ratios. It's 2 molecules of hydrogen and 1 molecule of oxygen. So we got to convert to moles because those are moles of particles, moles of molecules. So this conversion takes care of the fact that these ratios are not mass ratios. So 2.0 grams, 1 mole, 32 grams, 1 mole. And guys, I am still calculatorless. This I can do. Help me with 5 divided by 32. It's about a fourth. 0.2. Really? What did I do wrong in my... Oh, never mind. So 0.15. Is that right? 1.6. Okay. All right. So guys, now that we've converted to moles, we're still not done. Because now we need to respect the fact that these don't bond together in a 1-to-1 ratio. So in order to do that, we divide by coefficients. This divides by 2. This divides by 1. This is 1.25. This is 0.16. And at that point, we find out that oxygen is our limiting reactant. Yeah? Oh, good, thank you. From the balanced equation. So that's an understood, yeah, gosh, that was a big assumption on my part. Sorry. Yeah, the 2 and the 1 come from the balanced equation. Yep. So guys, does that sit okay? This idea of calculating limiting reactants? You feel good about that? Okay. So guys, with that said then, what we're going to do is then talk about one more concept, and then we're going to wrap this up. So guys, the final thing that we need to talk about is theoretical yields and then percent yields. So let me define this for you, and then we're going to move forward. So guys, a theoretical yield is the maximum amount of product that a reaction can form, given what its limiting reactant is. You okay? So guys, let me show you what we're talking about. You may want to scratch this down with me. So imagine that we take 5 grams of hydrogen and we take 5 grams of oxygen and we react them together. How much water can we make? In theory, what is our theoretical yield for water? Before you say a word, guys, think through what that thought process might look like. 5 grams of hydrogen, 5 grams of oxygen. How many grams of water will that make? What does that thought process look like? What do we need to know first? What do we need to know first? Yeah. Okay, so we need to know how many particles, so we'll convert to moles. Okay, what else do we need to know? So we need to know the ratio that they'll react in. We find that from a balanced equation. What else do we need to know? Yeah. There we go. So, guys, what's going to determine how much water fundamentally we can make? Which one do we run out of first? But guys, you'll notice that we figured that out right here. We already figured out that we're going to run out of oxygen first. So when we take 5 grams of hydrogen and 5 grams of oxygen and react them together, we already know that the amount of water that's going to be formed is going to be limited by the amount of oxygen, because that is our limiting reactant. Do you get the idea? So guys, what then might this calculation look like? Well, let's see if we can string this together. So remember, what we're trying to figure out is how much water can we form? Well, how much water can we form based upon burning up 5 grams of oxygen? Now guys, make sure you're clear on this. Why do we start with the amount of oxygen to figure this out? Because it's our limiting reactant. So this then becomes a theoretical yield calculation where we start with 5 grams of oxygen and we set our goal at grams of water. So let's do it. Do it with me. So guys, we're going to go 5 grams of oxygen, and what we want to know is how many grams of water can we produce? So guys, what does this calculation look like? Well, let's see. So we've got 2H2 plus O2 yields 2H2O. That's our balanced equation. So guys, how can we get from grams of oxygen to grams of water? Where do we go first? Matthew, you said it earlier. Got to go to moles of particles. So guys, our first conversion is going to be to moles. So 32.0 grams of oxygen is 1 mole of oxygen. So now we're in moles of oxygen. We're getting closer. But guys, we really don't want to study the oxygen. We want to study the water. So how do we get from moles of oxygen to moles of water? Where do we find that ratio? Go ahead, Meredith. Yeah, the balanced equation. So for every 1 mole of oxygen that we put in, we get 2 moles of water out. So guys, we're going to go 1 mole of oxygen in, 2 moles of water out. Then guys, can you finish it up? Where do we go next? Moles back to grams. 1 mole of water is 18 grams of water. And again, guys, I did order batteries for my calculator. Do you guys know about my calculator? Did I tell you about this? I got this guy when I was 16 years old. It's 34 years old, and it's still cooking. And the nice thing is that none of you know how to make it work because it actually doesn't work in English. And so when people steal it, they bring it back because they can't use it. You guys know about this? So it actually works in an engineering language called reverse Polish notation. Do any of you guys use RPN calculators? You all need to learn how to do, like if you guys are all headed into the sciences, someday when we don't have much to do, we need to talk about RPN calculators. These will save your butt in college. That's why engineers use them, because engineers chug numbers all day long. Those things are, I'll show you later. Okay, anyway, did you guys do the math? What's the answer? 5.6 grams? Okay. So, guys, this then is the idea. Don't miss this because this is about to get interesting. So, bottom line is this. If we burn up 5 grams of oxygen, we get out 5.6 grams of water. Let's make sure we're clear. Why did we start with the oxygen and not the 5 grams of hydrogen? It's our limiting reactant. Then we went to grams of water. And what we now know is that if we put in 5 grams of oxygen, 5 grams of hydrogen, we get out 5.6 grams of water. But what if we actually went and did this in lab, and we actually collected the water, and what if we only got out 4.7 grams of water? What happened? We lost some water. But then, guys, what we can do is we can calculate how well we did, and that is what is called a percent yield. And guys, percent yield is equal to actual divided by theoretical times 100. So our actual yield was 4.7 grams. Our theoretical yield was 5.6 grams times 100, and you can do the math. But guys, that then becomes the entirety of all of the stuff that we needed to gather up out of chapter 3. It actually ends with this idea of theoretical yield, at least given the stuff that you learned, or, well, it was a while, but learned last year. Literally 5 months ago. So guys, questions or thoughts about, we're not done, but questions or thoughts about anything we just looked at? You okay? Okay. So guys, I would encourage you to find a clean space in your notes, maybe flipping a page over or something like that. You now have 7 minutes to answer this question. You're given a balanced equation. Let me zoom into it. I don't want you to work with other people. I want you to get this done. You're given a balanced equation, and don't write down the question. You don't have time. I'll leave this on the screen. It says, assume that you use 25 grams of cyclohexane and 25 grams of oxygen. 3 questions. What's the limiting reactant? What is the theoretical yield for adipic acid? And then if you receive 33.5 grams of adipic acid, what is the percent yield? You now have 7 minutes to do this. Ready, go. So guys, as you're getting started, let me whisper in your ear. If you're reading this question and the first thing going through your head is, what the crap? Guys, understand you're not alone. The thing that you're working on right now is training yourself to do something when the only thing that's going on in your head is, what the crap? It could be setting a goal for your first calculation. Write a number 1 on the page and write down limiting reactant. And then think to yourself, okay, we just went over how do we calculate limiting reactants. Oh, right, we take the masses, we convert to moles, we divide by the coefficients. Guys, that's the critical thing right now, is developing a reflex that gets you past what the crap. So guys, we have 6 minutes left. I'm going to invest these next 6 minutes in trying to find somebody that can make this room less hot. So I will be back in 5 minutes. screencast. So, can we dig in? Okay. So, guys, when you started on this, the first thing that I suggested is if you're stuck, you need to come up with a strategy for coming unstuck. And I suggested that you write down a number 1 and you say limiting reactant and go from there. Guys, I would suggest to you that if you were stuck, there might be another reason that you were stuck that had nothing to do with trying to figure out what you were trying to do. But I didn't want to mention it to you then because I wanted you to have the experience of trying to come unstuck yourself. But guys, when you read through this problem, a lot of people get stuck on the 7th word in the stem of the question. Cyclohexane. You read through this problem and your mind, your eyes read the word cyclohexane, and first of all you struggle to pronounce it. But even if you could pronounce it, your brain then goes, even subconsciously, I have no idea what cyclohexane is, and therefore this is a problem that I can't solve. And then it gets even worse when you read through the questions and it says, what is adipic acid? And you have no idea what that is either. So guys, let's talk about some problem-solving processes before you even get started. Because guys, it turns out to answer this question, you don't have to know what cyclohexane is, and you don't need to know what adipic acid is. Why not? Because you know what oxygen is and you know what water is. Right? Guys, this is all about process of elimination. So if this is oxygen and if this is water, that leaves 2 things. And there's 2 things you don't know. Cyclohexane and adipic acid. But guys, how do you know that cyclohexane is on the left and adipic acid has to be on the right? Go ahead. Good. This is a yield. And yield, by definition, is a product. Products are yielded. So we know that adipic acid is the product. But guys, what if you didn't see that? How do you know that cyclohexane's on the left? Yeah? Yeah? Good. Good. So we're calculating a limiting reactant and we're using 25 grams of cyclohexane. Therefore, that's got to be the reactant. So the limiting the reactant is the cyclohexane, and then whatever that ridiculous thing is on the right, that's adipic acid. Guys, these are the kind of things that you need to get good at. These mental gymnastics that allow you to overcome things that are not immediately familiar. And guys, I know that the only thing worse than trying to do this in this really warm room is doing this at home when you're by yourself. Because frankly, you read over that question and your brain goes, what the crap? And then frankly, the next thing you do is you're checking your Instagram account because you're like, I got to do something that I can be successful with. Right? So guys, you've got to train yourself to go, no, I can't quit. I got to figure out how to figure this out. So, with that said, now that we know which is which, what are we doing first? Well, we're figuring out a limiting reactant. So guys, again, we've already looked at a calculation like this. I hope that you'll forgive me for chicken scratching this a little bit. So guys, let's talk about that. Is that okay? Guys, you do not need to write down chemical formulas necessarily in math. If it's easier to write down adipic than it is to write down that chemical formula, do it. That works just fine. Oh, it is? Oh, sorry. Unless it's not the thing that you're supposed to be writing down, and then don't do what I do. $70 to $84? Okay. All right, guys, I need numbers. How many moles up top? 0.1? 0.30 moles? What about down below? 0.16? We're okay. Okay, tell me again. I really need batteries for, yeah.
I was wondering if for hydrogen it'd be 1.11 for the...
Yeah, that's a really good question. And so again, the rule, the standard on the AP test is within one significant digit. And so probably yes, for hydrogen we should go 1.01, which is then 12.12, which then would make that 84.1. But understand, in either case, we're still within that significant digit. And to be honest with you, a lot of times when you're okay if you don't. But if you did, it's fine. Either way is fine. Okay, so guys, are those numbers correct to there? Okay, then dividing by coefficients, this is a 2, and this is a 5. And then we don't even need the numbers. Which one's the limiting reactant? Is it the cyclohexane or the oxygen? Is that right? Do you need to see the numbers? You know what? Give me numbers. So this is 0.15. What about that? Okay. Guys, common mistake. Let's talk about this. Common mistake is to stop the calculation there and stop. You would get 0 credit for all this work on the AP test. How come? You didn't answer the question. The question says, what is the limiting reactant? The question doesn't say, do the math to determine what the limiting reactant is. The question is, what's the limiting reactant? This question then, to be fully completed, needs a short sentence that says the limiting reactant is cyclohexane. Okay? Okay, now guys, moving along, the theoretical yield for adipic. Can I go? Okay. So we now have identified that cyclohexane is our limiting reactant. So then our next calculation then would start again with cyclohexane. I have no idea what I clicked on. So then, like so, and our goal then is grams of adipic acid. So guys, this is just a mass problem. So 84.0 grams is 1 mole of C6H12, and then 2 moles of C6H12 is 2 moles of adipic acid, and then 1 mole of adipic acid. What does that dude weigh? 146? And then, guys, what's the math there work out to? 43.5? Yeah. Hold on just 1 second. Hey, guys, hold on. A question on the floor. Go ahead. Yeah, because we've got a 2, and a 2. Yeah. Yep. And then, guys, my preference would be to not do the last calculation. It's simply asking for the percent yield. Can you picture it? Percent yield is equal actual divided by theoretical. Your actual yield is this. Your theoretical yield is the result of the mass problem. Do the math. What's the answer? 77%. You guys okay? Okay. So guys, with all of that said, and now, please. Oh, we need 3 significant digits, don't we? So 7, what was it to 3? What? 0.0? But again, we're within a significant digit, so we're okay. Okay. You guys good? Okay, so guys, this then is what tonight is going to look like. This is your homework now. So, sorry, just a second. Okay, here we go. So we've already started on this, right? What's left? Just the last three? Okay, so we're going to do that. Guys, in addition to that, grab your books. We are going to outline chapter 4. But this is not due until Friday. But guys, please turn to chapter 4 with me. And we're going to talk. Page 115. So guys, what you're about to receive is your first chapter summary assignment. What do you remember about these assignments as it pertains to your grade? They are here to save your butt, right? So guys, turn these in on time on Friday. Don't lose those points. But let me explain to you how this goes. If you don't remember, for the first half of the year, up until Christmas, every time we cover a chapter, I will prescribe the outline structure, the summary structure. This is the only time it will be an outline, because I want to start with something that you're probably familiar with. And then for the next 6 or 7 chapters, I'll be exposing you to other ways of interacting with scientific texts. So guys, bottom line is this. You have no choice in this. You have to outline chapter 4. If you choose something else, you're going to have to do it over. I want you to have the experience of doing this outline. So guys, with that said, starting on page 115, you'll notice that these chapters always begin with a pretty picture and a summary. Then when you turn the page again to 116, notice what you see. 4.1, that means chapter 4, big idea number 1, and then in big red letters, we'll call that red, big red letters, there's a big idea. Then guys, beneath that, you'll notice that without even reading words, beneath that, then you have the first subtitle. It says electrolytic properties. And then guys, as you allow your eye to, not reading words, but just scanning through the chapter, where is your next sub-idea underneath general properties? Well, over on page 117, ionic compounds in water. Then you turn the page again. Molecular compounds in water. Then strong and weak electrolytes. But then as you allow your eye to continue through the next couple pages, don't turn off 119. Guys, notice that you run into other words, big red words at the bottom of 119. But now you'll notice that this is 4.2. Do you see the structure? Guys, the idea here is that most scientific textbooks are structured like outlines. Let me explain to you what I mean. So guys, when you look at an outline, most of you know the general form of an outline. There's a Roman numeral that is the big idea. It's not the big idea for the whole thing. You could put a title on this, but then whatever the big idea is broken down into chunks. The first big idea is Roman numeral 1. This is big idea 1. And then beneath that, how do we denote the subtopics within big idea 1? How do you break down an outline? A's and B's. So you've got A, you've got B, you've got C, and so on. But then, guys, underneath the A, B, and the C, how do you then identify the ideas that make up the A's, the B's, and the C's? 1s and 2s and 3s. Now, guys, check this out. Go back to the first page of the chapter. There's your title. You're going to write this across the top of your outline. Chapter 4 is all about reactions in aqueous solution. Then you're going to turn the page. 4.1, general properties of aqueous solutions. That's your Roman numeral 1. Get it? Then what is the first idea under that big idea? Electrolytic properties. That's your A. Right? So that gets us to here. So guys, if you were fleshing this out, this is your first big idea. So this would be general properties of aqueous solutions. And then your A would be electrolytic properties. And then beneath that, all of the ideas, frankly, become the stuff that's in bold. Don't read, guys. As much as you can, don't read a scientific textbook. Scan through this and look for the big ideas, and those become your 1s and your 2s and your 3s. Then what becomes your B? Ionic compounds in water. And then whatever ideas you think are big under that are 1s and 2s and 3s. Do not write incomplete sentences. You are jotting down ideas. But guys, you're not chicken scratching like this. It's going to look good. I'm just hurrying. But then you'll turn over again. You'll have a C, which is molecular compounds in water. A D, which is strong and weak electrolytes. But then, guys, what about at the bottom of 119? Does precipitation reactions become an E? No, that's a Roman numeral 2. And you just keep going. You get the idea? So guys, no complete sentences, but you should have 1s and 2s and whatever underneath each of your letters that are underneath the Roman numerals. And guys, when you're done with this, you're going to have a summary of chapter 4 that fits on probably just a little more than a page or so. So that's going to be due Friday. One last thing. Guys, additionally, we're going to do this. On page 121, and this will be due next time, on page 121, in sentences, summarize table 4.1. Some of you should be working on this anyway because it's part of that quiz we talked about. We'll talk more about that quiz next time because some of you don't know what we're talking about. We'll talk. But guys, here's the deal. For next time in class, you're going to do this, you're going to do this, and then work on that towards it being due on Friday. Yeah. Yep. Isn't that on 121? Yeah, I got it. Yep. So again, guys, due on Wednesday, the last 3 questions and the summary of table 121. You can just put that as part of your homework. And then, guys, in addition to that, chapter 4, but that'll be due on Friday. You guys good? Okay, Kaylee, we'll see you. Have a great rest of your day. Guys, everyone else, get out of here. Go take a break. Get some fresh air.